This is called Newton's law of cooling. We're going to run through a pretty cool application, no pun intended, of exponentials. Now, if you do not know how to graph these, I'm going to give you about 20 seconds to look at the two of these. If you do not know how to graph these, you better make sure you're paying attention, because you're going to see these graphs over and over and over again next year and the year after, and when you take calculus and stuff like that. So there's a little hint over there. There are 3 key points on every exponential. Like I said, I'm going to give you about 20 seconds to think about that. I'm also going to remind you that E is called the natural number. It's also called Euler's constant. Okay? And it's about 2.71. So do you know the 3 points that we can use to graph the parent function of any exponential? Okay, don't say anything. Just raise your hand if you know what those 3 key points are. We got a couple of half a hands, a couple full hands. Okay, everybody take a look. Those 3 key points are this. If we're going to graph y equals b to the x, these 3 points always look exactly the same. It's -1, 0, and 1. This one's a 1, and this one is whatever the base is. And because this is a negative and we're going to put it in the exponential, it's 1 over whatever the base is. Whoops, thinking ahead here. So that's 1 over b. So this one is going to be, you can do this with every base, or every exponential, -1, 0, and 1. 4 of those 6 numbers, 4 of the 6 numbers in the coordinates are always the same. This one's going to be 1 over whatever the base is. So this is going to be 1 over e, and this is going to be e. So it's going to go through 0, 1. That's that kind of central point, if you want to think of it that way. This one's 1 comma e. E is about 2.7, so that would be about right here. And this would be 1 over 2.7, so it's around a third. You can think of it as 1 over 3, so it's going to look like this. And then we've got the asymptote over here. So if we were to put this on a quick draw, that would be a quick draw. That would be a sketch. If we wanted to convince people that we knew what we were doing, we might go through and label each one of these so they know, hey, this person really knows how we graph these. They understand exponential base e. This is called the exponential function. So if we put a negative in here, if we put a negative in front of the x, I could go through and come up with these coordinates. But what it's going to do is it's going to do a horizontal flip. When we multiply the function outside, it's a vertical flip. It reflects it across the x-axis. If we multiply the x by a negative, it flips it across the y-axis. So it's going to look like this. It's going to start up here, go to there, and then go down here. So that right there is what it would look like. There's our sketch, and I could label these -1 comma e, 0 comma 1, and this would be 1 comma 1 over e. You can make an argument for this because you could take each one of those x values, plug it in, and you'd get the right y value. Okay? If you don't remember how to graph exponentials that way, take a look at that. Consider this fair game for a quick draw or something like that. Okay? So, everybody got those? I slide down? All right, so here's the deal with what we're doing today. Okay, in the real world, nothing grows or decays in an uninhibited way, no limitations or anything like that. Usually, whether they grow or they decay, get bigger, get smaller, increase or decrease, there's usually some limit to it, so they eventually slow down and they stop to some degree. Okay, so let's see. If we were to do something like this, so I'm right here. So hopefully you guys are old enough that hopefully you've cooked in the kitchen or baked in the kitchen before. If you baked a cake, we normally put them in at about 350. If you take it out of the oven, put it on top of the stove, and then just put your hand right on top of it immediately, would you get burned? Probably. Yes, you would. Okay? Okay, the answer to that is yes. Okay? How long would it take before you could comfortably touch it? Would it take a couple minutes? Would it take a few hours? Couple minutes. It really doesn't take long. Okay, so I'm going to write not long right here. But if you've ever tried to frost a cake before it really cooled off, what happens to the frosting?
Not good stuff.
It just melts because it's mostly butter, right? So how long do you have to leave the cake out on the cooling rack on the countertop before you can frost it? Is it 10 minutes, an hour, or a couple of hours?
An hour, a couple hours.
It takes a couple hours for it to cool down. So when you first take it out, it is super hot. It's hot enough to burn you. A couple minutes later, thank you very much, you could put your hand on it and it would be hot, but it's not going to burn you. But if you want to frost it, which means it's got to get down to about room temperature, because even the butter that you might keep in your cabinet, if it's about room temperature, it doesn't melt. Now, if it gets 80 or 90 or 100 degrees, it might start to melt. Okay? So you've got to get that cake really cool around room temperature, and that takes a really long time. So look up here. Here's what happened. When we take it out and we click our stopwatch when we take the cake out of the oven, it's really hot. A couple minutes later, it's cool enough to touch, and a long time later, then it's cool enough that we can actually frost it. So we go from a really high temperature, goes off really quickly, and then it's going to come out here and it's going to kind of level off around room temperature. So if I do a graph that looks like this, and we think about what we've got at the top of the page, does it think that could be an exponential?
Yeah.
And would it be exponential growth like this, or would it be exponential decay like this? It'd be exponential decay. It's going to look something like that with a few adjustments to it. So this is called Newton's law of cooling. So put a star by this. If you can memorize this, that would be great. I'm telling you right now, we'll give this to you on the test. Okay, so you don't have to have this memorized, but you do need to know how to use it. So we're going to go through a couple examples and make sure we know how to use it, give you a short assignment, and that's it for today. So this is the temperature at any time T. The R right here stands for room temperature. The T naught is the initial temperature, just like we'd expect, all that other notation that we've used. Okay, and K is what we call the cooling constant. Now, if you'll notice that it says that K has to be less than 0. What that means is K is negative. If K is negative, that means the exponent is negative, and that's what's going to make it shaped like this. That's going to give us exponential decay like that. Everybody good there? You don't have to know all the insides and outs of this, but let's take a look at this and see how this works. So here's the formula, and we've got a cake. So on this one, it says a cake is removed from the oven and placed on a cooling rack in a 70-degree kitchen. The cake's initial temperature is 250 degrees. The cake can be frosted when it reaches 75 degrees. For this cake, the cooling constant is negative 0.025. So again, that cooling constant is going to be negative here. And finding that can be complicated. You'll learn how to do that in a couple classes from now. It takes a logarithm most of the time. Okay? So it says, even though the oven was set to 350 degrees, why did it only get to 250? Why would we take it out at 250? This is not a math question. This is like a science baking question.
Because that's when it was done.
D, thanks for raising your hand. What's that? Yeah, if we left the cake in until it got to be 350 degrees, just like it takes a long time to cool off, it would take a long time to heat up that far. All of the liquid, all of the moisture would be out of it. It would burn. It would be horrible to eat. Okay? We normally don't cook things until they reach the oven temperature. We've just had a couple holidays. If you bake a ham or a turkey or something like that, you bake it in a 350-degree oven, but you can take it out when it's about 165. That's the internal temperature that we're after so that it's cooked. Okay? So, even though, why didn't it only get to 250? Okay, didn't leave long enough to cook off all the moisture. You could say something like that. You could say, because it would be awful if it got to 350 degrees. Mason, real quick.
Does the mass of the object not play a role in like its temperature?
Depending on the mass and the way it's made, it would have a different cooling constant. Okay, which you'll see as we go through this. So it says find the cooling formula for this cake. So let's plug this in here. I'm just going to use a big capital T for this. Okay, Dane, what's R?
The rate.
Nope.
Oh. The percent.
Nope, got to pay attention. It's a big capital R in this, so it's room temperature. So it's 70 degrees. So this is going to be 70 degrees. Then it's going to be plus, and this is in parentheses. This is the coefficient in front of the exponential. It's going to be the initial temperature, which Caleb was what?
It was
250. This is T naught. So this is going to be 250 minus room temperature, which we already figured out was 70. And then this is e to the negative. In this case, they told us what the constant was. So negative 0.025, and then we put a t right there. Now, we're going to clean this up just a little bit. So here's the formula. We're going to do a big T of little t. So that's the temperature at time t. This is going to be 70 plus, and this is going to be a 180. Correct me if I'm wrong. And then this is going to be e to the negative 0.025 t. That is the formula for this cake. That's the cooling formula for this cake. Any questions? Okay, I got a question for you. The 70 makes sense. That's room temperature. What about the 180? Why is that a 180? We're just trying to figure out maybe why this would be in here this way. Zach?
That's how many degrees it has to go from how hot it was at the start and to room temperature.
Yeah, that's the difference between where it is and how much it's got to get down to room temperature. So that's why that's a 180. Okay? So we're going to say difference between how hot and where it will cool to, or something like that. Okay? So we're going to graph the function. So grab your calculator. So let's see, we're going to put in, that was 70 plus 180.
E.
I'm going to delete all that stuff. And we'll set up the window. So certainly don't need 10,000 on that. I'm going to go -2. And this is in, let's see, what's the time scale for this? That's important. This is in minutes. And that's the temp in degrees Fahrenheit. So let's maybe give it like 4 hours, 240 minutes. Scale, let's go by tens. And minimum temperature, I suppose we could use 0, but you could change that if you want to. And I'm going to put 300 because we know we have to at least hit 250. Okay, without hitting trace or anything. Has everybody got this in there? Okay, here's the question. Don't answer right now. Without looking on your calculator, hitting trace, this is kind of leveling off. Where is it leveling off? Andy?
70 degrees.
Why?
Because that's the room temperature.
That's the room temperature. Very good. Okay. If I put a little y-intercept right here, what would the y-intercept be? Without hitting trace, it's going to level off at 70. What's the y-intercept? Sorry, 250. So it's going to go like this. And it takes a long time to get down to that 75 degrees. So when can it be frosted? At 75 degrees. So I'm going to come in here. I'm going to change this to 75. I'm going to graph that, and we're going to make the calculator find it for us. Okay, so let's make sure we're clear on the units here. That's an x value. The y value represents temperature. We've got that labeled here. I learned that lesson the other day. Okay, what does that mean, Wilson?
It's gonna take 143 minutes for you to be able to ice the cake.
Very good. Okay, it's going to take over 2 hours, but almost 2.5 hours before we can frost the cake. Any questions? Yeah.
Can we put 2.5 hours?
2.5 hours, I'd be fine with that. Okay, but it did say we're measuring in minutes. Okay, what would happen if we let the cake get the same temperature as the oven? kind of already talked about that. It would be a brick. It wouldn't have any moisture in it. And how long would it take it to get to room temperature?
Let's check. So just
It
50,
never will.
350 minus.
Whoa, listen.
Shouldn't be this.
Sai, say that again.
It never will.
It never will, according to this mathematical model, because this is an exponential decay right here. It's got an asymptote. Does this exponential ever come down and hit the asymptote of 70?
My
No, does it get
calculator
super
says
close?
It does.
Okay. Dane's calculator says it does, but if he uses a little more decimal accuracy, you'll see that it's off.
Well, I can
Okay.
retrace.
All right.
Second calc.
Thank you very much. Okay, flip the page over. Got one more problem to do?
92 minutes.
Well, that's when it gets 70.0. That's when it gets too small.
Okay. Read example 2.
It's more like a warming function.
Ooh.
Excuse me?
Plus negative 10 plus 70.
So it was T of T equals room temperature plus then in parentheses T naught minus the room temperature, correctly? Or correct? And then K e to the KT. Now, this is the same cake. Mason mentioned mass and all that sort of stuff earlier. The same cake, whether it's warming up or cooling down, would have the same cooling constant. It has the same features, whether it's warming up or cooling down. If you have parents who are into physics and stuff like that, there's no such thing as cooling. There's only loss of heat. It's about heat transfer. It's not whether something gets cold or anything. Okay, so cold is like the absence of heat. So we can still use this, but we want to take a look at what happens with this. So this is going to be T equals 70 plus initial temperature, negative 10, minus the room temperature, 70, and then e to the negative 0.025 T, which if we simplify this, here's what we get. We get 70 minus, right?
Minus 80.
Minus 80 e to the negative, 0.025 T.
Ought to be a negative exponent.
Yeah.
It's always a negative exponent.
No
K
matter
is always going to be negative. Yep.
Why?
Okay. Hold on one second. When you put a negative in front of the function, when you multiply the function by a negative, don't say anything out loud. Let everybody think about this. When you put a negative in front of the function, what does it do to the shape? Don't say anything.
Decrease.
Hold on. And that version might make a little more sense. So here's my question. I'm pointing to this negative 80. What does that negative do to this shape right here? Okay, if this was a parabola that opened up, what happens if we put a negative in front of that x squared term? It flips it upside down. So this is a negative exponential. It looks like this. So we're going to take this graph and we're going to vertically flip it. It's going to look like this. It's still going to have a horizontal asymptote out here. So instead of this cooling down, we could say it's going to warm up like this. So grab your calculator, type this into your calculator and sketch this and label these. So remember, this is going to be minutes and this is going to be temperature. Sketch that and label it, and we can eat it when it's 50 degrees. Would you answer that question right there?
I know what frozen cake would taste like.
It's actually pretty good. Get your answer, check with your neighbor.
Heck yeah.
Yes, sir, Mr. Laws. Do we have any skips?
Multiples of 1.
Multiples of 4, guys.
So
Multiples of 3. Well, we're good.
Why does mine look so goofy?
Oh, goofy.
Why is yours below
Upside
the
down.
axis?
Because it's meant to be.
It's supposed to start below.
It's warming up.
Okay, but
here
Yes.
we go.
This is what mine looks like.
What?
mine looks like that.
Mine looks like this.
Maybe make the Y max more.
Oh, I just did negative 100 to 100 on both of them.
Use Zoom Fit. It's not hard.
How?
Just put the windows
Zoom
to
zero.
both. Just negative 100.
Oh, mine looks like this. Is that correct?
Is that the y-axis up there?
Yeah.
I would probably make it taller because we got to get up to room temperature.
That's what I'm saying. Mine is right.
What did I do?
I think mine
What
is right
happened
too.
yesterday?
What do you mean?
I was gone.
Oh,
A lot happened yesterday.
I watched the video. I just didn't want to do like the whole thing.
Oh, yeah.
But
I know somebody else like that.
No way.
Mr.
Well,
Wow.
I looked at like the odd solutions. I worked out how to do
Sweet.
it, but
I want to talk to you.
Okay.
It still doesn't.
How to help
Raise-
you? Time to get to class.
That's annoying. Okay, raise your hand if you know how long it's going to take for this cake to get up to 50 degrees. Okay. Lizzie, what do you got? 55.45 minutes. What'd you get? 55.45 minutes? Okay.
Winner.
Mine doesn't even get there. What
55.45 minutes.
How do you
I'm
do it?
so confused.
Okay, listen up. Okay, I want to hear. Hold on, not done yet. Listen up. Need to hear a big thank you on this. Did you notice the backside of this?
Yeah.
Well, this is my favorite